Go. All right, we're the Busy Bees, and we're studying chemosensory, looking at different morphological effects through robotics. My name is Derek Goulet, and I'm working with Percy Smith and Nick Bruno. Overview is we aim to develop a chemosensory feature to exist in Robogami robots through the following using the flow caps ratio and leakiness. What we did is construct different morphologies. As you can see shown on the right, we have a honeybee, a moth with low density around me, which are those hairs extending off, and a moth with high density. So we have three different types of prints. And what we did is we buried the distance to the odor source, the effective transport of that odor, and the concentration. And then we compared the resultant odor capture sensors mounted downstream to the one of a case with no sensor. We categorize this performance as a function of the flow capture ratio, source concentration, and distance. What this looks like is this uniform flow field with some sort of odor going past the antenna morphology and seeing the effects on the mounted sensor and just the robot body there.
So to briefly cover what our setup looks like in terms of communication between our electronic devices and the physical component of the antenna, the airflow would go through the antenna over top of the BME sensor, which is a Bosch sensor that measures humidity, pressure, temperature, and VOCs. And that will then send a signal back to our Arduino Nano, which will record the measurement in kiloohms as a function of resistance. And then based on the response that the Nano characterizes, it will tell the robot which directions to move by sending signal to the motors themselves.
Our main objectives for this project is really testing how morphology of insect antenna essentially affects the performance through relevant flow catchers or like its sensing capabilities. We would mount our sensor downstream and basically to show off the different amounts of odor flux coming to the sensor from these morphologies and hope to find essentially an optimal morphology. The biological principle that we're trying to translate here is leakiness or like relevant flow going through essentially an array of hairs or RAMI coming in to the sensor itself and seeing how much of an impact that has on the amount of odor an organism can sense.
Yeah, and to do that, we had conducted this discovery decomposition on a paper that goes through and addresses the leakiness and the flow capture ratio, which is basically leakiness normalized by the ratio of surface areas. So what that looks like is this hypothesis being tested here. They did an experimentation, and we found that leakiness and flow capture are both functions of Ramme density and velocity. And we looked to extend this by adding in odor. The analogy check, we had some dissimilar things. So we only had one sensor. We're not a distribution of sensors, but we overcame that by just making sure that it got the signal we wanted. And here's this other stuff. So we had a stiff 3D printed material, not flexible, but we noted that while we were experimenting as well.
So to briefly run through our experimental methods, we constructed a couple of different antennae based on honeybees and moths, 3 in particular. Then we mounted that sensor, our sensor downstream of the antenna, so that then we could measure the variability of the sensor response as respect to time and density of the plume, so that then we can characterize if the sensor is impacted by the type of antenna. The testing that we did required the robot itself, an odor source, and as a part of the robot, we also needed to have mounted sensors and antenna. We needed to consider the distance from the odor source to the robot itself. We did measurements at 5, 10, and 20 centimeters. We also did do 50 centimeters, but the measurements didn't end up working out correctly, so we did primarily focus on 5, 10, and 20. We had the fan set to 10 centimeters per second in terms of the transport of the odor source, and the concentration was held at 10 ppm of isobutylene. Then we compared the resultant sensor response across the morphologies and characterized that performance through evaluation of these different metrics listed down here. Typically, we'll show the way that we did set up the experiment. This here is a representation of the wind tunnel that we had. And as you can see, we were introducing airflow from the left-hand side along with the odor, which was the isobutylene. Then we had this honeycomb here to allow for the distribution of the airflow and odor itself. Then we had our robot an X distance away from the honeycomb with the sensor, antenna, and payload on top of it, the payload being the Arduino. We just continued varying that as a function of distance, and with the 3 antenna in the bottom corner. Then we also behind, as you can see there, we have the PID sensor that we use to check to see if our sensor was going to be reading values which we would expect at the distance that they were at, because we had validated that the PID was calibrated.
We use the wind tunnel to conduct all the experimentation for our robot. Now, on this end of the wind tunnel, we have a fan that powers all of the flow, so it just sucks the air through, and these wires are all fed to this power supply right here that's supplying 10 volts to this DAC that we're actually supplying from our computer, a pulse signal, and then also from this DAC we have it connected to what's called a photoionization detector, a PID, which is being used to ground truth all of our sensors measurements. What we do here is we go into the text section, we place the robot in, and then we put the fan on and feed odor through using this AlleyCat mass flow controller, where we have a set 10 parts per million isobutylene being fed into the system. And we run that for about a minute, get a reading on our PID and our sensor, and then we compare the two to make sure everything's ground truth. And then what we do is put in all of the different morphologies. And that's that for the experimental setup. Simulation methods. In tandem with the experimentation, we wanted a way to visualize this, and the easiest for that was to simulate it. So we created a domain of the wind tunnel where we had all of these boundary conditions for both flow and odor, and we had the odorant source down here, and we did simulations for both a neutrally buoyant, which would be a pheromone odor capture, so in a natural environment, and isobutylene, the gas that we had.
The testing protocol had 2 protocols altogether, one design and one failure protocol. The design protocol was mainly for sensor calibration, antenna stability, how we'd produce said design, and any possible personal equipment usage that we had. The failure protocol was mainly just for backups in case possible components were damaged or didn't really function properly, something like a backup battery per se. What we used is we had backup sensors, backup 3D printed antennas because they were very extensive with how small our RAMI were printed. And then overall a backup robot in case we'd possibly damaged it. And we stuck with our structure of 1.25 scale, which is what we've been using for most of the semester. And we kind of iterated this based off of multiple attempts throughout the semester. For the hypothesis validation, it was mainly determine it. What we did is we determined the odor flux and then cross-reference it with each antenna morphology and showing the variation in signal when exposed to the same pollutant.
Yeah, and to talk a little bit about the simulation results, we have a cross-stream slice that we can take through the middle of the wind tunnel, and on the left figure you see the neutrally buoyant plume or a pheromone, and it's just kind of emitting across. This is at 20 seconds. The right time slice, you see the isobutylene, which is immediately sinking to the bottom because it's almost 3 orders of magnitude more dense than air. So it's very, very negatively buoyant. And this is just to visualize kind of what was going on. So we knew that we needed to place the robot at the bottom of our tank. Quick animation of this. I won't show the whole thing, but this is just kind of the flow through the entire system. You have the concentration on the heat map, the vertical distance, and the downstream distance.
For the actual results and performance of our experiments, what we were able to create is a robot with, olfactory sensing capabilities that allowed for kind of an avoidance reaction if it sensed say something like acetone or a bad chemical, as we put it. The robot was able to detect concentrations ranging from 0 to 10 parts per million with about a distances of 20 centimeters away. And each antenna morphology itself maintained a different flow capture, primarily related to the RAMI density on the antenna morphology. On this graph, we can see that a lot of the flow catchers were lining up with the same same range as the moth flow captures, depending on the number of RAMI that we had. What we can see is that as we increase our RAMI, the X marks on the graph slowly get more and more in line with the theory and other previous experiments for olfactory performance, showing that adding an antenna upstream to the sensor did increase the olfactory performance of the given sensor itself.
Talk through some of the other plots that we looked at for performance metrics. This we wanted to characterize each antenna configuration by observing the statistics of the series using box plots of the time series. So these box plots show data grouped by the different antenna that we had present at one specific distance, and then pretty much looks over the entire time series that it was at that distance. As you can see, we on our y-axis have the relative gain in measured isobutylene. So we used the no antenna case to mark our baseline and then considered the change in predicted concentration of isobutylene to look at what the response looked like to better understand how the baseline value would change based on the different antenna that we had present. Then again, we looked at a different plot in this case, but this one we looked over the whole time series at percent change from the baseline value using the previously mentioned statistics, looking at how that changes as a function of distance over the course of all three different antennas. As we can see, there was a pretty consistent trend with regards to a decrease at 10 and then an increase overall as we reach 20. And the only one that we were really surprised by the behavior of was the 10 RAMI antenna. But overall, we think that it remained pretty in line with what we would expect from a sensor performance.
Yeah, and the significance for this is, knowing what orientation and shape works most effectively for a different regime, helps allow design of efficient sensing robots. You can think of, if they're in an operating environment indoors versus outdoors, you might want a different configuration because you have different background wind speeds. The sensors currently interact with the environment with no enhancement unless it's custom built. And we clearly have shown that some sort of obstruction upstream of the sensor, in the case of an antenna, will enhance that odor capture. So this also increases the range of application for low-cost sensors and air quality emissions testing. And we'd like to just highlight our references and thank you for the presentation.